Today we'll start matrix method of structural analysis. What is the objective of the analysis? The objective of the analysis is to determine the reaction at the forces in the members and the displacement of the joints. You may take a slope deflection method, Carney's method, or moment distribution method. In any method, you have to find out what that reaction you have to find out at support. Then you have to find out the forces in the members, and you have to find out the displacement of joints. So this is the objective of any method. So here we will start. That is the matrix method of structural analysis. So in matrix method, so we will discuss that is the flexibility matrix method of structural analysis and the stiffness matrix method of structural analysis. So there are two methods: flexibility method and stiffness method. What is flexibility? The flexibility of a structure is defined as the displacement caused by a unit force. So this is the definition of flexibility. The flexibility of a structure is defined as the displacement caused by a unit force. So let us take one single degree of freedom structure. So this is the example, single degree of freedom. So this is the spring. So here the end A is your fixed and end B is your single degree of freedom. The displacement takes place along this direction. The displacement takes place along the direction B. So this is one along this direction, one axial direction. The flexibility of spring is defined as the displacement delta 11 at the coordinate 1 due to unit force at coordinate 1. So what is the definition of flexibility? So this is the displacement delta 11 at the coordinate 1 due to unit force at the coordinate 1. When we will apply the unit force at the coordinate 1, this is the coordinate. When we will apply unit force at coordinate 1, so due to this unit force, so what is the displacement is your cost? So that is your called the flexibility of the 1 degree of freedom. So if a force P1 produces displacement delta 1 at coordinate 1, so what is the flexibility? So delta 1 by P1 is equal to delta 11. So this is the displacement due to the force P1. But this is the displacement due to the unit force. So the displacement due to the unit force, that is called the flexibility. And when the force P1 produced due to displacement delta 1, so this is delta 1 by P1 is equal to delta 11. This is called the flexibility. Similarly, so what is stiffness? The stiffness is defined as the force required for a unit displacement. Displacement required for a unit force, and here the force required for a unit displacement. Similarly, the stiffness of the spring is defined as the force K11 required for a unit displacement at coordinate 1. So here you see K11 is this is the force required for a unit displacement at coordinate 1. When we apply the unit displacement at coordinate 1, so due to that unit displacement, so what is the first force? That is called the stiffness. So P1 by delta 1 is equal to K11. So you can denote the flexibility, this is your delta 11, and you can denote the stiffness, this is your K11. So flexibility is equal to delta 11 is equal to delta 1 by P1, and the stiffness is equal to K11 is equal to P1 by delta 1. Now you are clear that is what is flexibility and what is stiffness. The flexibility is the structure defined as the displacement caused by unit force. But stiffness is defined as the force required for a unit displacement. When we apply the unit force here, so what is the displacement? And that is called the flexibility. And here, when we apply the unit displacement, so what is the force required for that unit displacement? So that is called the stiffness. Let us take one structural element with multi-degree of freedom. So this is one structural element with multi-degree of freedom. So this is your end A is your fixed, and here the B takes place the multi-degree of freedom. What is multi-degree of freedom? The displacement takes place in all directions. So here you take the displacement that is due to the 1, 2, 3, and 4. So 1 is your axial displacement, 2 is your transverse displacement, and 3 is your rotational displacement, and this is your 4 is your torsional displacement. Here you see the end B can have following 4 types of displacement. Here it explains 4 types of displacement. So first, due to the axial displacement delta 1 at coordinate 1, and second displacement along the direction 2, transverse displacement delta 2 at coordinate 2. Then the third one is your flexural or bending displacement delta 3 at coordinate 3. Then the fourth one is your torsional displacement or twist delta 4 at coordinate 4. So these are the 4 displacement takes place at the end B. The flexibility and stiffness of a structural member AB with respect to each of the 4 types of displacement that you have to find out. So first we'll take the axial displacement. When the axial forces are acting along the coordinate 1 in axial direction, so what is the flexibility and what is the stiffness that you have to find out. So if an axial force P1 is applied at coordinate 1, displacement delta 1 at coordinate 1 is equal to, you know. So when the forces are acting in axial direction, so what is the displacement? You know, in solid mechanics, delta 1 is equal to P1 L by A. So where L is the length of the member and A is the cross-sectional area of the member and E is the modulus of elasticity. But you have to find out what is the flexibility and what is stiffness. You have to find out here, because here the axial forces are acting along the coordinate direction 1. So you have to find out what is axial flexibility and you have to find out what is axial stiffness. You know from the definition of flexibility, flexibility is the displacement caused by a unit force. The flexibility with respect to axial displacement is obtained by putting P1 is equal to 1. So you have to take the unit force. So here the force is your P1. So you have to take unit force P1 is equal to 1 and the delta 1 is equal to delta 11. This is your axial flexibility is equal to delta 11 is equal to L by A. So this is the axial flexibility when the axial forces are acting along the coordinate 1. Then the axial stiffness of the member is force required for unit displacement. Then you have to find out the axial stiffness. So when you find out the axial stiffness, so what you have to do? So you have to put the displacement is equal to 1, and due to this displacement, unit displacement, so what is the force is equal? So that is called the axial stiffness. So K11 is equal to AE by L. So when you put delta 1 is equal to 1, then you have to take P1 is equal to K11. So K11 is equal to AE by L. So this is your axial stiffness. So when there you are acting the axial force along the direction 1, so you can find out the axial flexibility and you can find out the axial stiffness. So the axial flexibility is equal to delta 11 is equal to L by AE, and the axial stiffness K11 is equal to AE by L. Only you have to put here. So for flexibility, you have to put P1 is equal to 1. Then you have to find out what is, and delta 1 is equal to delta 11 L by A. And for stiffness case, you have to put delta 1 is equal to 1 and P1 is equal to K11. So K11 is equal to AE by L. So this is the axial flexibility and axial stiffness. Then the flexibility or stiffness with respect to axial displacement given by equation 1 and 2 are of relevance to members of pin jointed frame which carry axial force. So you see, already you know in structural analysis 1, so that pin jointed structure and the rigid jointed structure. So in pin jointed structures, so only there you are acting the axial force. Axial displacement takes place and axial force. So axial flexibility and axial stiffness, this is your relevance to members of pin jointed frame, which carry only the axial force. But in the case of rigid jointed frame, the axial displacement is very small as compared to the transverse displacement. So in the case of rigid jointed frame, to ignore the axial flexibility of the member, so you have to consider only the transverse displacement in this case and rotational displacement, but the axial displacement that you have to ignore in the case of rigid jointed frame. The members of rigid jointed frames are considered to be infinitely stiff with respect to axial displacement. That's why you have to neglect the axial displacement in the case of rigid jointed frame. Only you have to consider the transverse displacement and the rotational displacement. So then transverse displacement. So when the force P2 required at coordinate 2 for displacement delta 2 at coordinate 2 without any displacement at coordinate 1, 3, 4. Let us take here, you see, this is the coordinate 2. So when the force is acting along this direction, P2, and what is the displacement caused due to this force? Delta 2. And there is no displacement along 1, 3, and 4 direction. So this displacement is absent. Only the force is acting along the transverse displacement, and the displacement along this direction is your delta 2, P2 and delta 2. You know the relation P2, the force is equal to 12 EI delta by LQ. This is the relation, the force, and when the transverse force is acting along the coordinate 2, so this is the force and displacement relationship. P2 is equal to 12 EI delta 2 by LQ. So by definition, the flexibility and stiffness with respect to the transverse displacement is, so you have to find out this case, what is the transverse flexibility and what is the transverse stiffness. So you know what is the flexibility, what is flexibility? So this is the displacement caused by a unit force. So you have to put the unit force here. So in the case of transverse flexibility, you have to take P2 is equal to 1 and the delta 2 is equal to del 2. So here del 2 is equal to L2 by 12 EI, LQ by 12 EI. Similarly, you can find out what is the transverse stiffness. So in the case of what is the definition of stiffness? So this is the, what is the definition? This is the force required for unit displacement. So when we put the displacement is 1, delta 2 is equal to 1. So P2 is equal to K22. So K22 is equal to 12 EI by LQ. So this is the transverse stiffness. This is the, so only you have to remember that is the flexibility, displacement caused by the unit force, and in the case of stiffness, the force required for a unit displacement. This only you have to remember this one. This is the relation you have to take, and you have to put P2 is equal to 1 in the case of transverse flexibility, and this is equal to delta 2, and in the case of transverse stiffness, you have to put delta 2 is equal to 1, and P2 is equal to K22. K22 is equal to 12 EI by LQ. So this is your equation 4 and 5 are based on the assumption that the end A is your fixed. So this is your equation is when the end A is your fixed. End A is your fixed. This case, this is end A is your fixed, and the transverse displacement here is equal to, this is the transverse stiffness and transverse flexibility is equal to this. If far end A is your hinged, let us take the end A is your hinged. So when the end A is your hinged, so that case, so what is the that case, the relation between the force and the displacement is equal to P2 is equal to 3I delta 2 by LQ. This is the force P2 required at coordinate 2 for displacement delta 2 at coordinate 2 without any displacement at coordinate 1, 3, and 4. So this is the relation between the force and displacement when the far end A is your hinged. So by definition, so you have to find out what is the transverse flexibility, and you have to find out what is the transverse stiffness. So transverse flexibility delta 2 and transverse stiffness K22. So what you have to do in the case of flexibility? So you have to put displacement caused by a unit force. In the case of flexibility, this is your displacement caused by a unit force. So you have to take P2 is equal to 1. Here you have to put P2 is equal to 1. So when you put P2 is equal to 1, so delta 2 is equal to L3 LQ by 3I. Similarly, in the case of stiffness, so what you have to do? So this is your force required for unit displacement. This is the force required for unit displacement. So what you have to do here? So you have to put displacement is equal to 1. So that force is equal to the transverse stiffness. So when you put here delta 2 is equal to 1, P2 becomes K22. K22 is equal to 3I by LQ. So this is the transverse flexibility and transverse stiffness when the far end is fixed. So this is the transverse flexibility, transverse stiffness, and when the far end edge were hinged, so this is transverse flexibility and transverse stiffness. Then when there you are acting the bending or flexural displacement, you have to find out here. So when the moment you are acting, so the moment you are coming in the case of flexural case. So when the bending moment you are acting, due to that bending moment, what is the bending or flexural displacement? So this is the relation between the force and the displacement. In the case when there you are acting the bending moment, flexural displacement takes place. The force P3 required at coordinate 3 for displacement delta 3 at coordinate 3 without any displacement at coordinate 1, 2 and 4. So here the force is acting P3 at coordinate 3, and due to this force the displacement takes place delta 3 at coordinate 3, but without any displacement at 1, 2, 4. So this case, so 1, 2, 4 there is no force, no displacement, only the force is acting at the 3 coordinate, and the displacement due to that force is your delta 3. You see here, so this is the third force, the flexural bending. So here the bending moment, when there is acting the bending moment, so due to that bending moment, so what is the displacement takes place? When the moment is you are acting here, so due to this moment, the displacement is your rotational displacement. That you have to take the relation between this, the moment and the rotational displacement, and there is the other forces along 1, 2 and 4 direction is your absent, and the displacement are also along 1, 2, 4 direction is also absent. Only the force is acting in the direction 3, and the displacement is you have to find out along the coordinate 3. Due to this, you have to find out what is the flexural flexibility, and you have to find out what is the flexural stiffness. You see, so this is the relation between the force and the displacement. So you know that is the rotational displacement already. You know that mv is equal to 4ei theta by L. You know bending moment due to the rotational displacement. This is the relation. So here the moment you are taking here force P3, and the displacement theta is you are taking here the delta 3. So P3 is equal to 4ei delta 3 by L. So by definition, the flexibility and stiffness with respect to flexural displacement is, you know, that is displacement caused by a unit force. So when you put here the force is equal to 1, so delta 3 is your delta 3. Displacement caused by a unit force. P3 is equal to 1 and the delta 3 is your del 3. So del 3 is equal to L by 4A. Similarly, stiffness, you know what is the definition of stiffness? Force required for unit displacement. So here you have to put the displacement is equal to 1. So due to this unit displacement, what is the force required? For this unit displacement, what is the force required? So that you have to take K33, and this is your 1. So K33 is equal to 4ei by L. So this is when far end A is your fixed. And when far end A is your hinged, so this case, the force and the displacement relation, this one. P3 is equal to 3i delta 3 by L. So here also you have to find out what is the flexural flexibility and what is the flexural stiffness. So by putting P3 is equal to, and the delta 3 is equal to L by 3a, and for flexural stiffness, you have to put delta 3 is equal to 1. So P3 is equal to K33, K33 is equal to 3a by L. So this is the flexural flexibility and the flexural stiffness when they are acting the flexural moment, the bending moment. So due to that bending moment, the rotational displacement takes place, and due to this, you can find out the flexural flexibility and flexural stiffness. So when there is your end edge you are fixed, and there is end edge you are hinged. Then coming to the flexibility matrix. So what is your flexibility matrix? You are clear that is what is flexibility and what is stiffness. Then in different cases, when you are acting the axial force or the transverse force or the bending force, so what is the axial flexibility, axial stiffness, and transverse flexibility, transverse stiffness, and flexural flexibility and flexural stiffness. Then what is the flexibility matrix? Let the system of forces P1, P2, P3, Pn acting on the structure. These are the forces acting on the structure. So due to this force, it produces the displacement delta 1, delta 2, delta 3, delta n at coordinate 1, 2, 3, 4, n. This is the coordinate 1, 2, 3, 4, n. And the forces are acting P1, P2, P3, Pn. And due to this force, the displacement takes place delta 1, delta 2, delta 3, delta n along the direction of the coordinate. Then using the principle of superposition, the displacements delta 1, delta 2, delta 3, delta n may be expressed by the equation. So delta 1 is you can find out by using the principle of superposition. Del 1 1 P1 plus del 1 2 P2 plus del 1 j Pj and del 1 n Pn. Similarly, you can find out that delta 2 is equal to del 2 1 P1, del 2 2 P2, plus 2 del 2 j Pj, del 2 n Pn. Similarly, you can find out del n, the displacement nth coordinate is equal to delta n is equal to del n1 P1, del n2 P2 plus del nj Pj plus del n Pn. In the case of flexibility, the displacement required at coordinate 1 due to unit force at coordinate 1. So delta 1 1 indicate the displacement cost at coordinate 1 due to unit force at coordinate 1, delta 1 1. Similarly, if you take this one, del 2 2, so displacement cost at coordinate 2 due to unit force at coordinate 2, del 2 2. Similarly, this one, del I2. So displacement cost at coordinate I due to unit force at coordinate 2. The second one is your unit force and first one is your the displacement I2. So this is the force here. So this is the total displacement in coordinate 1. So this is the force due to unit force at coordinate 1. So what is the displacement? This one. So this is the flexibility. Here also, so due to the unit force at coordinate 2, so what is the displacement? So this is the also flexibility, delta I2. So del I is equal to del I1 P1 plus del I2 P2 plus del Ij Pj plus del In Pn. You can write this in matrix form. In equation 1, this is your equation 1, this one. Del Ij is the displacement at coordinate I due to unit force at coordinate j. Already I have explained this one. So hence del I1 P1 is the displacement at coordinate I due to P1. That is the force due to P1. This total. Similar del I2 P2 is your displacement at coordinate I due to P2. Hence the total displacement at coordinate I due to all the forces may be expressed as del I is equal to delta I is equal to del I1 P1 plus del I2 P2 and del In Pn. So this is the total. So you can write this simultaneous equation, the force and displacement relationship in the matrix form. You can write delta 1, delta 2, delta 3 up to delta n. This is your column matrix, and you can write del 1 1, del 1 2, del 1 j, del 1 n. Similarly, del 2 1, del 2 2, del 2 j, del 2 n. Then del I1, del I2, del Ij, del In. Then del N1, N2, Nj, Nn. So this is you have to write in a matrix form, and the force P1, P2, Pj, Pn. This is also column matrix. So this is called the displacement matrix, and this is the force matrix, and this is the flexibility matrix. This matrix is called the flexibility matrix. You can write this expression. So delta is equal to del into P. So this one delta a column matrix. This is your column matrix. This is a column matrix of order n into 1. N number of row and 1 column. Here n into 1 means n row. The row is your n, but column is your 1. So that you can denote by n into 1. Then P is also a column matrix of order n into 1, known as force matrix. So this is your called the displacement matrix, and this is your force matrix, and here also the order is your n into 1. Then del is your a square matrix of order n into n. This one is your square matrix of order n into n, del nn. Square matrix of order n into n, known as flexibility matrix. So this is your called this matrix is your called the flexibility matrix. So you can find out the displacement at different coordinate. If you know the flexibility matrix, what are the forces acting at different coordinates? So using this matrix, you can find out what is the displacement at different coordinates. Delta 1 is equal to del 1 1 P1 plus del 1 2 P2 plus del 1 J Pj and del 1 and Pn. So this is this equation. This equation you can rewrite in the matrix form, and from this matrix form you can find out what is the displacement at different coordinates. So it may be noted that the element of the jth column of the flexibility matrix are the displacement at coordinate 1, 2, 3, 4 and due to unit force at coordinate j. Hence, in order to generate the jth column of the flexibility matrix, a unit force should be applied at the coordinate j and displacement at all the coordinates determined. So this displacement constitute the element of the jth column of the flexibility matrix. So now you are clear that how to find out the displacement at different coordinates. So by using the flexibility matrix. So these are the forces P1, P2, Pi, Pj, Pn, and these are the displacement. So by multiplying this square matrix, the flexibility matrix and the force matrix, so you can find out what is the displacement at the different coordinates. Then coming to the stiffness matrix, let the system of forces P1, P2, P3, Pn producing displacement delta 1, delta 2, delta 3, delta n at 1, 2, 3 and coordinates. If a unit displacement is given at coordinate j without any displacement at other coordinates, the forces required at coordinate 1, 2, 3 n may be replaced by K1j, K2j, Knj respectively. Thus, Kij is the force at the coordinate I due to unit displacement at coordinate j. Here you can find out the total force Pi at coordinate I due to displacement delta 1, delta 2, delta 3 and up to delta n, and may be computed by using the principle of superposition. Here also you can find out Pi is equal to Ki1 delta 1 plus this is your Ki2 delta 2 and this is Kin delta n. So what does it mean? Ki1, so this is the force required at coordinate I due to unit displacement at 1. Here you can write the equation P1 is equal to K11 delta 1 plus K12 delta 2 plus K1j delta j plus K1 n delta n. Similarly, P2 is equal to K21 delta 1, K22 delta 2 plus K2j delta j plus K2n delta n. Then Pi is equal to Ki1 delta 1 plus Ki2 delta 2, Kij delta j plus Kin delta n. Pn is equal to Pkni n1 delta 1, Kn2 delta 2, Knj delta j plus Kn delta n. So this is your equation 4. So you can rewrite this equation in the matrix form of the force and displacement relationship. So here this is the force matrix P1, P2, Pi, Pn. So this is the column matrix, and delta 1, delta 2, delta I, delta n. This is also the column matrix. This is the displacement matrix, and the square matrix, the inner one. This is your called the stiffness matrix. So the order of the stiffness matrix is your n into n. And the force matrix, this is your n into 1. So this is your n number of row versus 1 column. And then the displacement matrix, this is also n into 1 order. So n number of row and 1 column. So this you can denote, that is your the force matrix P, and the stiffness matrix you can write K, and the displacement matrix, this is your delta. So P is equal to K into delta. So K is a square matrix of order n into n. This is your known as the stiffness matrix. You can denote the stiffness matrix this manner, that K11, K12, K1j, K1n, K21, K22, K2j, K2n, Ki1, Ki2, Kij, Kin, Kn1, Kn2, Knj, Kn. So this is the n into n, so the square matrix, this one. So in order to generate the jth column of the stiffness matrix, if you want to find out the jth column of the, let us take any one column. This is the first column. The second subscript indicate the column. So this is the first column. This is second column. This is your jth column. This is jth column and this is nth column. So in order to generate the jth column of the stiffness matrix, a unit displacement must be given at coordinate j. So you have to apply the unit displacement at the coordinate j, and due to this unit displacement, so what is the force required? So that indicate this K1j, K2j. Force required at all the coordinates determined. At the coordinate 1, what is the force? Due to the unit displacement j. Similarly, K2j, so this is the force at the coordinate 2 due to unit displacement at j. Similarly, if you take the Kij, so this is the force required at coordinate I due to unit displacement at j. So that you can find out. The forces constitute the element of the jth column of the stiffness matrix. In order to develop the stiffness matrix, a unit displacement should be given successively at coordinate 1 to n. Unit displacement you have to give at coordinate 1 to j n, and you have to find out what is the forces due to that unit displacement. Here you see, so this is K11 means, so the force required at coordinate 1 due to unit displacement at coordinate 1. And when we take K12, this is the force required at coordinate 1 due to unit displacement at coordinate 2. And K22, here the force required at coordinate 2 due to unit displacement at coordinate 2. So here you can find out finally the force P1 is equal to, so when they were due to the unit displacement at coordinate 1, due to unit displacement at coordinate 2, due to unit displacement at coordinate j, and due to unit displacement at coordinate n. So you can find out the total force by the principle of superposition. So P1 is equal to K11 delta 1 and K12 delta 2, K1j delta j, K1n delta n. Similarly, you can find out Pn for n coordinate. Pn is equal to Kn1 delta 1, Kn2 delta 2, Knj delta j, and Kn delta. This is known as the stiffness matrix. Now you are clear, that is, so what is flexibility matrix and what is stiffness matrix.